It's my great pleasure to introduce tonight's speaker, Shawn Willsey. Shawn did a talk for us almost 2 years ago to the day, and we're really happy to have him back. Shawn is a distinguished professor of geology at the College of Southern Idaho. He's taught there since 2004, so almost 20 years. He has a Bachelor of Science in Geology from Weber State University, Master's in Geology from Arizona State. Northern Arizona University, sorry. Shawn prides himself on being an effective communicator, which I'm sure you will all agree with at the end of this talk, and brings geology to the general public. He is the author of 2 amazing books, which I highly recommend. Hopefully the Zoom audience can see that too. Roadside Geology of Idaho and Geology Underfoot in Southern Idaho. And having just used one of these books, the one for the Grand Canyon, they are really, really helpful and really instructive. He has a YouTube channel, which I got to preview some of this talk on and said, please do this for us. He's a licensed professional geologist in Idaho, has led geological field trips for groups throughout the West, as well as the ones who want to go on, Iceland, Hawaii, and Scotland. In addition to geology, Shawn teaches whitewater rafting and rock climbing at CSI and is a licensed climbing guide. He lives in Twin Falls with his family, and we're very fortunate to have him here. Please join me in welcoming Shawn Willsey.
Thank you.
Oh, before you start, Shawn.
Yeah. Whoops.
Could you show your books again? People on Zoom are having a hard time.
Yeah, I actually have a slide with them.
Oh, okay.
How do I, Cynthia? Oh, get rid of this top thing.
Other more.
Yep.
Hide floating meeting controls.
Oh, thank you. Sweet. Great. Well, thank you for having me. Happy to be back. The last time I was here 2 years ago, it was via Zoom. So it was a little easier to do, obviously sitting in my computer office. It was an odd way to do it though, because I'm giving a presentation, but I'm doing it in my office with no one there. So this feels more real, having a little more energy in the room and actually faces to look at, because I was just talking to my computer and hoping that the system and the technology was working. So this is great, and I appreciate the opportunity. What I'd like to do tonight is talk to you a little bit about the Bonneville Flood, something you probably heard about. Maybe you know a lot about it, but I think I might be able to add some insight and some perspective and some knowledge that maybe you don't have. Maybe there's some holes in the story in your mind that I can help fill in. And I'd like to also convey, as I do this with the Bonneville Flood, why I think it's one of the great geologic events in Western North America that's been largely, and by no fault of anyone, but it's been somewhat pushed under the rug a little bit. And I'll kind of come back to that point at the end of my talk. And talking about the books real quick that Mike mentioned, and they're available here if you want to, but just real quick before we get into the Bonneville Flood, the first book here, Geology Underfoot, is a book about 23 unique locations in Southern Idaho. Tells you how to get there, specifically where to go. The idea is to get people out of their car, engaged with the landscape. Maybe you're hiking a trail, maybe it's a road cut, maybe it's an overlook. This is a series of books put together by Mountain Press Publishing in Missoula, Montana. And so this book is nice because you can see the map there with the 23 dots. And there was a lot to choose from in Southern Idaho, but ultimately I settled on those 23 places. Some you've heard of, like Craters of the Moon or City of Rocks, but maybe a few you haven't heard of, like Spence Gulch or Leeton Gulch, or maybe Box Canyon, which might not be familiar to folks outside that area. So that's available, and that's a great resource if you're visiting that area, or you just want something to either put you to sleep at night or maybe learn some geology from a new area. And then the roadside geology book is probably one you're familiar with. I think they've got most of the states covered. There's a few I think they're still working on. This is actually a second edition. The first edition came out in the 80s. It was black and white. It was well done, but we've learned a lot in the 30+ years since it came out. And so me and 2 other geologists in the state revised that edition with full color maps, brand new text, just the whole meal deal, just a complete revision of that book. So that's a nice one as well, as you maybe take travels or adventures into that part of the state. And then lastly, as just something else that Mike mentioned, my big passion as a professor, as a geologist, has not been in so much research. I know you get a lot of researchers here sharing their expertise with you. That's not really what I do and what I'm passionate about. My main job is teaching geology in a college setting, but I found my calling in finding ways to convey Earth's amazing stories with the general public. And so the books are one avenue and one way I've kind of pursued that. But another way that I've come to realize is really effective. And so I guess, thank you, COVID, for this sort of thing, because it was when COVID kind of hit everyone that I realized I couldn't take students on field trips, and I was looking for something else, you know, to bring the field trip to them. And so I started a YouTube channel, not really knowing what to expect, having no idea what I was doing. I still feel like I don't really know what I'm doing, but what I found is that it resonated with a lot of people, and that me just going somewhere in the field and looking at things and observing and explaining things as best I can works for some people. So that might be something you look at. And there's other people doing this too. I'm not the only guy on the block, but anyway, so that's out there too if you're interested. So, okay, so the Bonneville Flood. Let's see what we can glean from this story. For me, this is the most comprehensive overview I've ever done. I've done a couple little presentations on the Bonneville Flood, but in getting ready for this evening, I've got a lot to share with you. I went out this last week and got drone pictures, and I did a big deep dive into the Bonneville Flood. So the Bonneville Flood story starts with the story of an area, a region, and it starts with the story of a lake. So it starts in this region of the West we call the Great Basin, basically from the Wasatch Mountains of Utah westward to the Sierra Nevada of California. This is an area where faulting and extension of the crust, basically east-west stretching of the crust, has produced a series of faulted basins, low areas, and intervening mountain ranges. And if you've ever driven across Interstate 80 on your way to Reno, you know what it looks like. There's a mountain, then a valley, then a mountain, then a valley. So in the process of this area, and that's probably a whole nother topic for another presentation, but the basin and range has produced a region where water in many of that parts of the Great Basin does not drain out to any other river body or to the ocean. It's an enclosed basin where water is trapped within that basin for the most part. So you can see during the last geologic period, the Pleistocene, you can see the extent of some of these freshwater lakes that existed in the Great Basin. And the largest of them, the biggest one of all, was this one that covered much of western Utah, a little bit of southern Idaho, and even easternmost Nevada. And this is this lake known as Lake Bonneville. So Lake Bonneville was huge. It was as big about as Lake Michigan. So it had it, you know, if it existed today, it would be another Great Lake, I suppose, or the West Great Lake. It has an interesting history where it had lakes in it throughout the last, we can trace it back to about 800,000 years. It probably had lakes prior to that as well, going back further in time, but it for sure had lakes within it during that period of time. Of course, Lake Bonneville was its sort of high stand when it was all sort of one water body. But if you can imagine the water going up and down, not all the water would be interconnected. So you would end up with a series of lakes rather than one large connected lake. Interestingly, most of the basin's history, as we look at the geologic record, most of the basin's history is similar to today. So most of Lake Bonneville's history is a few little lakes and salty lakes, like the Great Salt Lake is today, versus having large freshwater lakes. So the anomaly is having the freshwater lakes and a large lake system, but that's the one we're going to focus on today. So of course, today's Great Salt Lake is, you know, no offense to the Great Salt Lake, but it's really just a salty puddle. It's really just what's left behind from Lake Bonneville. Lake Bonneville was a freshwater lake because the climate was cool enough and wet enough that there was so much water coming into it and not enough water lost to evaporation that it stayed a freshwater water body versus the Great Salt Lake of today, which is salty because water comes into it, but so much more water is lost to evaporation that process concentrates the salts and the other elements in it. So you end up with a salty water body rather than a freshwater body. So it's huge. It was absolutely massive. I guess from Jackson Hole, it wouldn't have been more than a few hours drive to get down to the shores of Lake Bonneville. It would have been a little rough for our friends in northern Utah because all the major big cities along the Wasatch Front were completely inundated and covered at times up to 1,000 feet deep by Lake Bonneville. So Lake Bonneville was studied first by G.K. Gilbert in the late 1800s. He was a sort of a pioneering geologist in the West, someone that really could look at the landscape and interpret it and made great interpretations. For the most part, the things he discovered well over 100 years ago hold true today. We don't really see a lot of flaws or misinterpretations in the things he concluded. And the Lake Bonneville is probably greatest evidence to the casual observer as you're driving around the Wasatch Front are its shorelines. And so you can see here in this top photo, at least two prominent shorelines on this hillside here. In the bottom left photo, you might be able to pick out a few more. So he recognized these shorelines. He recognized that there was a large lake that existed in northern Utah at some time in the past. And he was able to trace those shorelines throughout northern Utah and eventually trace it to a critical point in its extent, which is this area called Red Rock Pass, which is in southeastern Idaho, which we'll look at in a few minutes here. He was also able to recognize that that was the point, that was the location where this lake overspilled its banks and created a massive flood. So he recognized that well over 100 years ago, which is pretty amazing. And so his interpretations still hold true today. So this is a simple graph from a recent publication. It's a little bit odd because it starts with the older time frame here on the right, and as you move left, it moves towards more modern time. But what we can see is about 30,000 years ago, the lake was about similar to the modern Great Salt Lake in terms of its elevation or altitude. And then we can see the lake rising, so at sometimes quite steeply, other times a little more gradually. And then you can see drops and rises and drops and rises. But basically from 30,000 years to about 18,000 years or so ago, the lake was rising in a really remarkable way and increasing its extent laterally, increasing its depth. And then right at about this point here, about 17,400 years ago, 18,000 years, somewhere in there, there's this marked drop just vertically, just the lake drops about 300 feet, about 100 meters or so. Then it rises a little bit, and then it drops pretty steadily until we end up with the modern Great Salt Lake. So this is a nice little summary of what the lake was doing over the last 30,000 years. And we're going to focus partly on why it rose so high. And then we'll spend most of our time looking at what happened here, what happened when the lake overflowed and when the Bonneville Flood was initiated. So the question is, why did it rise so high? And climate was part of it. So this lake being enclosed in a basin, if you had periods of more moisture and less evaporation, then it would make sense the lake would rise. If you had periods where it was drier and more drought-like conditions and more evaporation and less water coming in, it makes sense for it to drop, right? So I think the climate accounts for some of the variation, but this really steep rise demands a bigger explanation. Because if you look at the Great Salt Lake today, or the entire Lake Bonneville Basin, it's really not fed by a lot of big rivers. The biggest rivers that go into the Great Salt Lake today are the Provo, the Weber, and the Jordan River, which drains out of Utah Lake. And those rivers, if you look at their outputs or their flow, it's not really impressive. And so there has to be another reason why the lake rose so high that it overtopped its extent and precipitated this massive flood that we're focusing on tonight. So where is that story? What was the reason for Lake Bonneville to overspill its banks, to not only rise, but then ultimately to overspill its banks? Well, the answer to the question is a river that probably doesn't get as much attention as it should. And this is a river called the Bear River. If you look at a map of the Bear River, it drains out of the Uinta Mountains, which are in northeastern Utah. The Uinta Mountains during the last ice age were extensively glaciated. They are high mountains, well over 10,000 feet, going up to over 13,000 feet in elevation. There was a large drainage system and a lot of water and ice and snow up there. And the Bear River takes a path, and this is true today, right along the Wyoming-Utah border, kind of dances back and forth between the two. Then it cuts into Idaho just north of Bear Lake. And prior to 55,000 years ago, the Bear River flowed into the Snake River directly. So the Bear River was part of the Snake River drainage basin. Now, how do we know that? Where does that evidence come from? Well, an interesting thing about this part of the story is not only the geologic evidence is there, but an interesting sort of side note here is that biologists looking at the DNA of fish, and I'm way outside my lane right here because I'm talking about biology, so bear with me. But when they look at the DNA of different types of trout and other river fish species in the Bear River today, it does not match what they see with other fish that are part of the Bonneville Basin, part of northern Utah area. What it matches most closely with are fish species that are today in the Snake River system. And for the longest time, the biologists were scratching their heads like, this doesn't make sense. These two rivers don't even connect. They're separated. How would these fish species have a similar ancestry as we go back in time? And at some point, the geologists got involved and waved their hands and said, hey, we can help you. We know the answer. We can help figure this out for you. And so what happened is the Bear River flowed along this path prior to about 55,000 years ago. But then something happened. The Bear River got diverted. And you can see, so this is the path the Bear River takes today. Notice again, it flows for a couple hundred miles right along the Wyoming border. It's making a beeline for the Portneuf River, which goes into the Snake River. But then right near the town of Soda Springs, it does a complete 180, a complete hairpin turn in its course, and now flows south. And today it goes into the Great Salt Lake north of Ogden. But during Lake Bonneville time, it would have joined the lake just southwest of Soda Springs, right about here. And so the big question will be, well, why would a river do that? Why would a river stop flowing in one direction and flow in some other direction? Well, here in Jackson, not too far from Yellowstone, how many talks have you had about Yellowstone, right? Well, here's another Yellowstone connection, okay? So the Yellowstone hotspot, I know you're probably all familiar with that. I live here in Twin Falls, and here's the progression of young volcanic rocks getting younger to the northeast towards the modern Yellowstone Plateau. But there's a weird anomaly. The chemistry of all these rocks here in southeastern Idaho is very similar to the basalts we see in the Snake River Plain. Now, we don't have a good explanation for this, but somehow the generation of magma that fuels these Snake River Plain volcanoes is actually also erupting at times in the past in this southeastern portion of Idaho, this area called Gem Valley Volcanic Field, or sometimes called the Gem Valley Blackfoot Volcanic Field. So these areas here have a really similar chemistry that ties them to the Yellowstone hotspot. But why they're erupting way over here is a good question and something that's being researched. It may have something to do with the faulting, basin and range extension, some of those things. We're going to focus on the southwestern portion of this volcanic field, what's known as the Gem Valley Volcanic Field. And if just as kind of a bit of reference here, if you see where my little arrows pointed, here's the Bear River. So right about here is where the Bear River makes this big swing to the southwest into the Great Salt Lake, or what was then the Bonneville Basin. And this is what it looks like. This is looking northeast towards Soda Springs. It's just over this ridge here. The Bear River is hugging the north end of the Bear River Range. That's this mountain block here. I'll show you some other pictures from ground view here in a second. Here's one of the cinder cone volcanoes that exists in Gem Valley. So this one's called Old Crater, very original name. And just some information on these. There's a lot of different types of volcanoes in Gem Valley. They consist of shield volcanoes, which are just big lava flows that extend out in all directions, forming a big kind of low profile dome. There's cinder cones, which tend to be a little bit steeper and erupt more pyroclastic material like cinders. So it's throwing out little clots of airborne lava. It has fissures, so cracks in the ground where the lava poured out. And it even has some volcanoes at the south end of Gem Valley called tuff rings. And tuff rings occur where magma interacts with water. So these are a little bit different. I'll show you a photo here in a second. They tend to be much wider in diameter, not as high as like a cinder cone, and much more explosive because the water and the lava are interacting. So we know that the eruptions in this region, in this part of southeastern Idaho, range from about 430,000 years to about 55,000 years ago. And it wasn't erupting all the time as you'd expect. There were intermittent eruptions, but it has this very concentrated history of eruptions between those two ages there. And what we think's going on, Suzanne Janicki at Utah State has done some research here and has put forth the idea, and again, it's just a hypothesis, maybe it's right, maybe it's wrong, but she believes that there was just a real fine balance between the Bear River, the faulting that was going on, because there's a large normal fault, the East Gem Valley Fault that runs north to south through the valley, and all the volcanic. So if you have volcanoes erupting lava, a river trying to get through the landscape, and faults moving the land up and down, I think you can see how those three entities would be kind of conflicting and fighting over the same real estate. And this is a common theme, not just in this part of Idaho, but where I live as well, is that whenever an eruption occurs, where does the lava want to go? Downhill, right? And what's the most downhill thing in any location? Typically a water body or a river, right? And so the Bear River has been diverted probably multiple times over its history by these eruptions. And so what she sort of postulates is that the Bear River at times was going north to the Snake River, and then there'd be a little eruption or a faulting event or something that would shift it ever so slightly, just bringing the land up or down a few feet, that would divert it back to the south, and then it would get diverted to the north. And so there was a period of time where the Bear River was moving into both basins incrementally, depending on what was going on with these different players, volcanic activity, faulting, and the river itself. Just a couple other views here. This is looking straight north. So you can see this fault scarp here. So this fault, let me go back one real quick. This fault is active because it has created a bench or an escarpment, a little cliff on the surface of the earth. That lets us know that this fault has produced earthquakes and faulting probably over the last few thousand years. I don't think it's had a historic fault in modern or earthquake in modern time. There's that same crater we were looking at, but now I've swung over to the north a little bit. There's another cinder cone here called Alexander Crater, which is quarried and used for road base and other construction materials there. There's the main highway going east to west across the valley there. Another view, so this is further south. I told you that one of the volcano types in South Gem Valley are these things called tuff rings. There's my little van down there for some scale. So this crater here that they put a pivot in and they're irrigating, so works well, right? Farmers in Idaho are innovative, if nothing else. But this is actually a low rim of pyroclastic material. This is evidence that a volcano erupted either in groundwater or in shallow water, and the lava water interaction made it behave much more explosively. As the lava heats up the water, it flashes to steam. That's a volume increase, and so it tends to be much more explosive. In a similar fashion, I guess, to like a geyser in Yellowstone, I suppose. So we have all these different volcanoes in Gem Valley. Here's a little better view of the fault. So there's the fault scarp. So now we're looking north. The fault is oriented, so it's west dipping, which means the right side or the east side is the upside, and the left side or the west side is the downside. And it's cutting through some of those basalts. So I'm not sure the age of this specific basalt. This might be, I think this is the 55,000-year-old Soda Point basalt. And you can see it's cut by and offset by the fault there. So that lets us know that the fault is younger than the lava flow there, than that basalt flow. So the point of these slides is just to show you the volcanoes, the faulting, and how the little interplay between those two occurring more or less simultaneously over this interval might have been a trigger or the main trigger that diverted the Bear River. All the geologists agree the Bear River gets diverted into the Bonneville Basin and Lake Bonneville by about 55,000 years ago. Not controversy, but the thing we don't know is like, well, was it flowing to the north for a while, then the south, or was it just one event? So we don't know the details in terms of how that diversion actually occurred over time. Here's a view. This is called Soda Point. So this is the Bear River swinging around the north end of the Bear River Range and then flowing back all the way another 150 miles into the Great Salt Lake. So this is where it's making its hairpin turn. Everything in the foreground here below the label Bear River is all that basalt, all that Pleistocene lava. And this is common. What we tend to see is when a lava flow occurs where there's a river, the lava flow takes the channel of the river. The lava basically takes over that landscape, that real estate from the river, and then the river usually gets diverted to the sides of the lava flow, and it starts eroding and entrenching a new canyon and a new channel along the sides of it. So you can see here some of that Soda Point basalt, 55,000 years, and then again the north end of the Bear River Range with that limestone there, the Cambrian Ordovician limestone there. So you can see that the excavation that's gone on. The Bear River's cut down maybe about, oh boy, I didn't measure this, but it's probably maybe 70, 80 feet. So like, I don't know, 30, 20, 25 meters, something like that in that 55,000 year interval. This is a nice diagram, and I couldn't find the reference, so I apologize to whoever published this. I searched long and hard to find who put this together, but this is a nice summary of the whole event taking place. So if you start with the left diagram here, we can see the Bear River coming across through what's now Soda Springs, and then heading across Gem Valley and joining, I mean, it says it's joining the Portneuf River, but the Bear River was the biggest river. The Bear River was a massive river. And so really this was the ancestral Bear River, and then flowing off to the northwest, ultimately into the Snake River north of Pocatello. And then what you can see here is with the dotted line is that we can see the little volcanoes here. So the volcanoes are erupting possibly during this time period here. And then possibly at other times, the Bear River would have been diverted south into the south part of Gem Valley. And at that time, it actually would have formed a lake, Lake Thatcher. So this was, Lake Thatcher is well documented with some shorelines and some other sediments and evidence. And this would have been the final resting place of the Bear River. The Bear River would have flowed into this basin for a period of time. And then eventually it maybe would have shifted back to the north. And then ultimately though, Lake Thatcher overflowed and started cutting a narrow valley. It's called the Oneida Narrows. This is just north of the Utah border. And then that would have flowed down into the Great Salt Lake. And then with the last diagram here on the right, you can see what's more or less what we have today, the full integration of the Bear River across the north end of the Bear River Range, down into the south end of Gem Valley, and then down into Lake Bonneville. So Lake Bonneville would have extended everything you see in blue there at that time, even up into the south end of Gem Valley during its high stand. So the idea here is that the Bear River is a huge river. Even today, the Bear River accounts for, I think, like 60, 70% of all the inflow into the Great Salt Lake. Now, today's Bear River, like a lot of rivers in the West, including our beloved Snake River, which we kind of share in common, it's here in Jackson Hole, and I'm a long ways downstream in Twin Falls. But like a lot of rivers in the West, the Bear River has been extensively diverted for irrigation and other uses. And so when you see the Bear River today, if you're heading down to Salt Lake City and you drive over it near Brigham City, you might think to yourself, that's not much of a river. How about that Shawn Willsey guy told me that caused the Bonneville Flood? I'm not impressed. Well, trust me, the Bear River would have been a massive river at that time, just a huge river. So if you add a huge river, bigger than any other river going into the Bonneville Basin, you add that huge river to a basin that has no outlet, it's inevitable that the lake's going to rise dramatically for some period of time. There's maybe some climate fluctuations in there, but ultimately you're reaching an unsustainable position where the lake at some point is going to overflow and spill over. And that, of course, is the Bonneville Flood. So the Bonneville Floods, breaching point was here. If you look at the map here on the top left, the little red circle there, that's the location of this threshold, or this location for the spillover, which is known as Red Rock Pass. And you can drive up, I think it's Highway 91, goes right through there. There's a little sign, but this is what it looks like. And this is what it looks like a few days ago. So it's beautifully green, no filters there. If you go any other time of the summer, it probably looks a little more yellow. But let's take a look at why this location, why Red Rock Pass, what was going on there? Well, here's the highway down here in the valley. And so everything just on the left edge of the photo there, that would be the Bonneville Basin. That would be to the south. That would be going down towards Lake Bonneville, essentially. If you go to the very right edge of the photo, you're entering the Snake River drainage. So this is the drainage divide. This is the pass, or the high point between these two drainage divides. Here we are looking to the west in the photo of the Bannock Range. And there was a prehistoric ancient landslide that I've delineated here in yellow. So you can see this kind of lumpy, bumpy ground where this section of the mountain range slid down. So we had part of the Bannock Range slide down into the valley. Okay, and if we swing around and look to the east or the northeast, we have a drainage up here, Marsh Creek. And what I've shown here is a big alluvial fan, a big depositional feature, whereas the stream has flowed down into the valley over probably a few million years, or at least thousands of years. It's deposited sediment and made this big triangular, or mostly triangular shaped fan. So when you come back down to the Bonneville Basin and look to the north, we're looking right at Red Rock Pass there. And we're looking actually at these two locations where they coalesce. So the Bannock Range is to the west or the left here. And so there's part of that slide. Now my view's not perfect here, so things look a little askew because things are kind of in front of each other, a little bit of foreshortening, I guess. And then what I've done here is trace in an approximate level of the alluvial fan. So that black line is more or less closely, I think, the topographic surface that would have existed before the Bonneville flood. Lake Bonneville would have been lapping up against that black line, that shoreline right there, about 17 to 18,000 years ago. Of course, the Bonneville flood, when it happened, it eroded a lot of that soft material and cut down into it. And you can see this about 300 or so feet of erosion that's occurred since that time. In the process, it's excavated and exposed older rocks that were buried in the subsurface. So I hope that that's clear to you, is that we had an alluvial fan coming in from one direction, a landslide from another, and that's what created the topography that existed at Red Rock Pass prior to the Bonneville flood. Now imagine in your mind's eye, water flowing over the top of that. We've got landslide deposits, just a bunch of rocks and sand and sediment loosely, just loose. We have an alluvial fan on the other side, same sort of thing. And I think you can see how once you get water moving across that loose material, it can start to erode it, it can excavate it, and it can start to create a domino effect where the downcutting of the lake as it's overflowing becomes sort of a precipitous process where it just kind of dominoes from there. So the Bonneville flood. So now we've looked at the lake. We've looked at the location of the spillover and some of the geologic conditions that existed prior to the Bonneville flood. For the number geeks in the room, here's some numbers for you. For most of you, it's like, I can't quantify or fathom that number, right? And that's probably me. So how much water did the Bonneville flood release? You can see the number there, about 1,200 cubic miles of water, about the volume of Lake Michigan. Basically, Lake Michigan emptied into Idaho in probably just a few weeks, maybe a few months, which is pretty incredible. That volume of water flowing down the Snake River during that period of time. At its peak discharge, so in terms of how much water it's carrying per second, cubic feet per second, if you want to use those units, you're looking at about 35 million cubic feet per second. That's 5 times the average flow of the Amazon River. So during the Bonneville flood, the largest river on planet Earth was the Snake River, right? Was the drainage out of Bonneville, Lake Bonneville, and into the Snake River. This was the biggest river on the planet for a short period of time, but still, we gotta hang on to whatever cool superlatives we can. Yeah, the age of the flood there, which we talked about. The duration is tricky. It's all estimates based on hydraulic modeling. hard to get, there's not a lot of datable material. You're trying to date how long the flood lasted, but really all you can do is look at how much water spilled out of the basin, where that water went, how big the channel was that the water spilled through, and just make some crude estimates. But probably weeks to months, maybe a year of like high near peak discharge would be the time frame we're looking at there. So an incredibly short duration flood. When we get to the end, some of you might be thinking about another flood, a more famous flood, unfortunately, that also occurred in the Pacific Northwest, and I'll compare the two at the end. So if you're like, well, how does this stack up with this other flood, which shall not be named? I'll mention that a little bit in the end. And probably the best thing, or maybe the most spectacular thing that the Bonneville flood did, was dramatically alter the landscape that it passed through. And in places where there was already a canyon that was narrow, it eroded. It reamed out that canyon. It made it wider. It made it deeper. It plucked rocks the size of your car and even bigger and flung them downstream. In places where the path of the Snake River was already wider, all those big rocks that it just removed got deposited or dropped. And so I'll show you some photos of those. This is Shoshone Falls at high flow. I just needed a nice little piece of eye candy to go with all the numbers. So, but here's the path of the Bonneville flood. So we've seen Red Rock Pass. We know the Bear River now being integrated into Lake Bonneville. So the flood came down Marsh Creek. That's the drainage that comes out of Red Rock Pass. Marsh Creek comes down to the north near McCammon, where it joins the Portneuf River. And they actually join a little bit closer to Inkom, which is up here. Then it blasts through a narrow spot near Pocatello called Pocatello Gap or Pocatello Narrows. Dramatically altered the landscape in Pocatello where it widened out. It joins the Snake River here. There was actually already a lake, a Pleistocene lake where now American Falls Reservoir exists. Well, as the Bonneville flood came into that lake, it quickly allowed that lake to rise. It overtopped its natural dam just downstream, and all that water came down through places like Massacre Rocks, down towards the town of Burley, the area I live in, Twin Falls, westward. We'll hit a couple of these places along the way, but south of Boise, eventually going through Hell's Canyon, and then beyond my map, joining the Columbia River and all the way out to the Pacific Ocean. And we see evidence for the Bonneville flood from Red Rock Pass all the way to the Columbia. So the evidence for it is really dramatic in many locations. This is what the floodwaters do in places where the water is flowing fast and concentrated, maybe through more narrow spaces. It strips away the topsoil. And what it does with in a lot of places, what we have in terms of a underlying rock is basalt, which is a very hard, dense volcanic rock. But the power of that water and the gravel and the sand and the boulders that it's carrying basically polishes that rock surface and leaves striations or lines, grooves in it, similar to a glacier. So it has that similar kind of power as the water passes over it. And you can see this in so many places along the path. This is a photo looking, this is I-15. So Pocatello is just a few miles back towards your view, back up the road there, looking south. And what I thought was kind of cool and striking here is that you're on top of a set of cliffs here. It's a little hard to see, but these are big boulders that were not just transported down this valley, but moved up onto this bench. I put the elevations here to kind of help out with this. So there's the drainage basin today, about 45, 30 feet. And here's these boulders a good, I don't know, 125 or so feet higher. So again, pointing to the power of the flood to move these boulders. And I didn't put scale in here, but some of these things are up to 6 feet, 2 meters in diameter, just absolutely massive boulders, not just being rolled along the bottom, but in some places actually being deposited up on these benches. So the name we give these boulders, the big boulders that were transported by the Bonneville flood actually have a formal stratigraphic name that's used by geologists. They're called melon gravels. And so some people are like, why melon? Why the name melon? And these actually came from this sign. This sign still exists. It's probably from the 50s, at least, I would guess. It's this old Stinker gas station. If you walk to the back of the sign, it says Stinker gas station. Those gas stations don't even exist anymore, but the sign's still there. And this is what the sign reads. So petrified watermelons, take one home to your mother-in-law. And then behind the sign is a field of Bonneville Flood transported boulders that in places are about the size of a watermelon. And so there you go. It became kind of a fun joke, but that's where the name melon gravels came from, is the watermelon connection there. So we're going to go downstream to a place right near my hometown. So we've gone west from Pocatello. Here's kind of the overview map at the top, just to kind of keep you oriented here. So we've got Red Rock Pass here. We've come down Marsh Creek. We've looked at some of the features there. Through Pocatello, I could have picked so many places to show you photos of remarkable features, but we're now here in South Central Idaho between the towns of Burley and Twin Falls. And in this location, the Bonneville Flood did something interesting and quite unique. All the water was coming down the Snake River. Now, the Snake River already had a canyon there. A lot of people where I come from in Twin Falls think the Bonneville Flood made the Snake River Canyon, and that's not true. The Snake River had a canyon. It was just a lot smaller. So as the Bonneville Flood came into this region around the town of Burley, this area is kind of wide and open. There's no real canyon there, but starting right here where the modern day Milner Dam is, this is where the Snake River Canyon proper starts. And it extends all the way down to Twin Falls. Of course, Twin Falls is famous because there's a big canyon there. People jump off with parachutes off our bridge, usually end up safely descending to the bottom. Evel Knievel even tried to jump the canyon once upon a time in the 70s with his rocket-propelled motorcycle. So there is a big canyon from Milner Dam downstream to Twin Falls and beyond. So imagine all that water coming downstream and trying to get through this constriction. All that flood water is trying to get through the constriction at the start of the Snake River Canyon where Milner Dam is today. And you can't get all the water through quick enough, right? So the water's going through, but there's so much water still coming into the system that the water starts backing up. And so the water backs up and floods this entire region near Burley. We call this the Burley Basin, until finally the water doesn't know where it's supposed to go or where you would like it to go. The water takes the easiest path of least resistance. And so the water actually, as some of it was coming through the Snake River Canyon, the water eventually found an alternate channel to the north. And so it flowed overland across these lava fields and the sagebrush plains of this part of the Snake River Plain. And then near Twin Falls is where this channel, what we call the Eden Channel, actually rejoined the Snake River. And it's in this region where we see some of the most spectacular erosional features. There's estimates from Jim O'Connor at the USGS and some other folks that during the Bonneville Flood, most of the water actually went through the Eden Channel. Maybe 70% of the floodwaters went through this secondary path versus going down the Snake River proper. And it makes sense. If you look at the width of the Eden Channel, it was probably 20 to 30 feet deep. The water is probably moving at like 20, 30 miles an hour. It's a big, big area. And the reason why it was separated from the Snake River is there's some shield volcanoes. And that's what these buttes are here. Skeleton Butte, Hazelton Butte are big shield volcanoes, high topographic features that the water was forced to go around. So for the most part, this is the only place along the Bonneville Flood's path where the Bonneville Flood left the Snake River Channel and went some other direction, flowed in some other path that it had previously not flowed along. So let's give you a little view from the air. If you get on Google Earth, so here's, to orient you, here's the interstate right here, the Snake River and the Snake River Canyon shown there. We're looking to the west. You can see all the farm fields, and then there's this area where they're not farming. Well, why not? There's no soil, right? I'm no farmer. I grew up on Air Force bases, but I do know this much. You need soil to farm, right? If you plant a seed in solid basalt, you're probably not going to get much out of that. And so you can actually see this swath of area, and this shows up so nicely on like satellite views in Google Earth, where the Eden Channel came through, where this path of the Bonneville Flood flowed overland across this sagebrush plains here, stripped away all the topsoil, and even started stripping away and excavating some of the basalt bedrock that lies underneath. Here's another view. So you can see the Eden Channel coming in from the right here. Here's the interstate. Here's Twin Falls proper, the town. But if you look closely, you'll see a couple other things in the landscape. You'll see things like Blue Lake's Alcove, these big horseshoe-shaped canyons surrounded on three sides by sheer cliffs of basalt. This doesn't make sense. Like, you know, if you look at this from any other perspective, what removed all the rock? Why would you have this sort of horseshoe-shaped canyon there? And if you look closely, you'll see there's a lot of these. The one at Devil's Corral is a little bit different because it's more tiered and stair-step rather than having one big drop. But this is where, to me, this is where some of the best action from the Bonneville flood occurred, is where this channel came back into the Snake River. So here's Devil's Corral. These are all plunge pools. So you can see as the water came back in, it would have flowed into the Snake River, but as it started cutting up rocks, I mean, the hydraulics of this flood sort of are beyond comprehension. I'm a whitewater rafter. This was, and we have a scale for whitewater rafting that goes to class 5. This was class 10 whitewater. I mean, this is like insane vortices and eddies and hydraulics that you just can't even quite fathom because the scale was so kind of mind-blowing. And that had the power of actually chewing up that bedrock, getting into the fractures of the basalt, plucking pieces of the rocks out and removing them. So this was an erosional process. This was excavating and removing rocks out of the canyon. And so this is one neat little area near Twin Falls called Devil's Corral. Here's a view. So you can see the interstate kind of back up here. You can see a few of the cars on the interstate. And you can see here, it's more of a stair-step pattern. But again, there's no flowing water there today. There's no streams that come into this. This is solely the product of the Bonneville flood and its erosional capacity. Now we're here in Twin Falls at the Perrine Bridge. So this is where the base jumpers jump. And you can see all the layers of basalt here, but there's that vast Eden Channel. So this is what we call it's a scabland. It's just an area of exposed and eroded bedrock, in this case, basalt with very little topsoil above it. Another kind of view swinging around, there's the bridge again. And you can see this big bowl here. So this was just basically a huge plunge pool with water circulating in it, just insane. And we can see here that the basalt is actually a little easier to erode than the underlying rhyolite. Near Twin Falls, the canyon exposes two rock types. Younger basalt, this one's about 95,000 years old, the one along the rim. And then below it is about 8 million year old rhyolite. And that rhyolite comes from a time when Twin Falls was sitting right above the Yellowstone hotspot. So we were producing rhyolites and a very different rock type because of that volcanic history. And that's probably another presentation for another time. But again, just to see some of the erosional landform features here, just pretty incredible. Perrine Bridge looking down to the west, so you can see the Snake River Canyon and its width here, but you can also see some of these big embayments, these big erosional scars on the landscape. This is Blue Lake's Alcove, and a lot of these cut down deep enough that it intersected our water table, and so a lot of these have really beautiful crystal clear blue cold water springs that emanate from the bottom of these, and this is actually where we get a lot of our local water supply. Comes from some of the springs there. And there's a golf course if you're a golfer. So there you go. A little bit of everything. Similar kind of view here, except the main thing to look at here is some of the erosion that the flood did along the floor of the Snake River Canyon. So you can see here this little mini canyon, what we call a paleo channel, carved out by the flood. So the flood actually carved out a little secondary channel at some point during the Bonneville flood. So many cool features to see. This is a little further west. We're kind of just heading west and downstream overall. This is right off the freeway, maybe about 30 miles west of Twin Falls, looking at this big boulder bar. So it's a little hard with the scale here, but some of these boulders are Volkswagen size, 8, 9, 10 feet in diameter. You can see the Snake River there. We're looking south. Going a little further west, even at Bruno Sand Dunes, which is covered in obviously sand, there are exposures of a lighter deposit of sediments. And when you look at these up close, and this is one of the little places I point out in my book. Oh, sorry, sensitive. You can see some of these ripple marks in here. And this is a big embayment, a big, call it Eagle Cove, but this is a place with an old meander scar in the landscape. And the floodwaters came through here, but wider canyon, the water had slowed down. It wasn't moving big boulders at this point. it was mainly just moving sand and silt. And in this big embayment, the water kind of swirled and settled a little bit and deposited some of those silt and sand sized particles, but had just enough movement to it that it produced some of these ripples you see here. So just another great place to see some of the Bonneville Flood's handiwork in action. This is one of my favorite places. This is south of Boise. This is one of the biggest boulder bars from the Bonneville Flood, called Walters Bar. But this has the added bonus of also being a location where Native Americans actually drew on it with petroglyphs, inscribing different symbols, figures, that sort of thing, in the desert varnish on some of these boulders here. So you can see some of that. And this is Idaho's only, I think I got this right, Idaho's only archaeological park. It's run by Canyon County. So it's called Celebration Park, and there's trails there and all sorts of boulders with all sorts of interesting little figurines and hieroglyphic kind of features on it, but all on Bonneville Flood boulders. Another view of the same thing. There's me next to one of the bigger boulders, just to give you again a sense of scale. And then the other thing you can see here is the angle of the boulders, right? What we call imbrication. So in this case, the water would have been moving from left to right across that photo. You can see the orientation of the rocks just kind of laying over like they were dominoes. And then we'll end our story down here in Hell's Canyon. And thanks to my co-author Keegan Schmidt up at Lewiston for giving me some photos for this presentation here. So down in Hell's Canyon, which is part of the Snake River, one of the deeper canyons in all of North America, we have not only deposits of the Bonneville Flood in Hell's Canyon in places, but also large ripple marks. So you can see these mega ripples, not just on a small scale, but on a meter or tens of feet type of scale, which is pretty impressive. And the Snake River flowing, in this case, to the north there. And then last thing here, this is near Lewiston, but this actually is one place where you can see the Bonneville Flood and the Missoula Flood and their age relationship. So these are Bonneville Flood sand and gravels here in this gravel quarry that I guess has been excavated, unfortunately. And then sitting on top of that are some of the deposits from the Missoula Flood. When it backed up into the Snake River drainage, it actually had some finer grain deposits that were placed down right on top of the Bonneville Flood. So this shows you that the Bonneville Flood predates the Missoula floods that occurred in the Pacific Northwest. And then just one more shot kind of showing those up a little bit closer. So in conclusion, Bonneville Flood, unfortunately to a lot of people, is the ugly stepsister to the Missoula Flood. The Missoula Flood's the big one you hear about. Anyone in the Pacific Northwest knows all about the Missoula Flood, the Ice Age, and maybe it's more exciting and sexy because it had a glacier involved with it. I don't know. People like Ice Age stuff and they like glaciers. I think there's just a lot more people living there. And so there's more interest in their backyard than the Bonneville Flood. But there's a quick little recap here in terms of the numbers of floods. The Bonneville Flood was a singular event. The Missoula Flood, holy cow, they're still trying to figure it out, but there seems to have been at least 40 episodes of the Missoula Flood. And if you're not familiar with the Missoula Flood, the quick recap is the ice sheet covering Canada and the northern fringe of the US crept down into western Montana, blocked up the Clark Fork River, creating an ice dam that backed up into the area around Missoula. The shorelines in Missoula are really obvious, but then eventually that ice dam breached. That lake completely emptied, scoured out eastern Washington with a massive flood called the Missoula Flood. And then after the flood ended, the ice would creep back down, block that same river again, create a lake. It gets breached, and that occurred over and over and over again. And maybe 40, maybe more than that, floods occurred in that region. You can see a comparison of the volume of water. The Bonneville Flood released more water. It released more water than any one of the biggest Missoula floods. But the Missoula Flood actually had higher discharge. It actually flowed faster, if you want to think of it that way. It had a lot more erosional power than the Bonneville Flood. Timeframes, you can see those there. And then, yeah, the Missoula Flood was actually faster. They think that whole lake was emptied within just a few days. And then here's my last thing here. I thought I was going to look up papers written on the Missoula Flood versus papers written on the Bonneville Flood. but that was just overwhelming and I couldn't figure out how to do that. So I'm like, let's just look at books. Let's just look at published general public books on the Missoula floods. Our National Park Service even has created the Ice Age Flood, a national geologic trail in that area. And I don't, kudos to them. I think that's great. I'm all for geologic education. And then I counted at least these 6 books on Amazon that you can buy that have something to do with the Missoula floods. Then I did the same thing for the Bonneville flood. And this is what I got. So in conclusion, I feel like the Bonneville flood deserves a little more scrutiny, not just from the scientific community, but the general public. It deserves a little more attention. It has equally spectacular landforms and evidence that are very accessible to anyone that's interested in looking. I guess we just need to work on getting the word out a little bit better. So you're now all my ambassadors, my Jackson Hole friends, about helping educate people about the Bonneville flood being just as spectacular and as amazing of a geologic event as the Missoula floods, which get all the acclaim for some reason. So, and that's all. Thanks for your time. Appreciate it.
Full question.
Okay, sure.
Obviously, everyone, people in the room will have questions.
Sure.
You'll also have to alternate with the Zoom audience.
Okay.
And basically, Bob Tilling will collect questions.
Okay, well, we'll start with the audience, the
We'll kind of
in-person.
alternate.
Okay, all right.
Oh,
Yes, sir. Question.
Time frame of the flood and the erosion is still in several weeks. Is that correct?
Yeah, that's the estimate, weeks to months. Oh, yeah, the question was, is the time frame of the Bonneville flood in the kind of weeks range? Yeah, that's the best estimates right now based on the modeling. The geologic field evidence, we just don't have the age resolution to resolve that.
So all the erosion we're looking at photographs done in weeks or
Yeah, which makes the Missoula flood even more impressive that you look at, and now it had more floods, but any one of those did a lot of erosion in just a few days. So this is where the earth, which we usually think of as doing things at a very slow, snail's geologically slow pace, this is where we have a more catastrophic, massive event and faster processes. Yeah, good question. Yes, sir.
is the basin still
Yeah, I guess so. I guess the question was, sorry, the question was, if you filled the Bonneville Basin with water again, would the low point of overflow be Red Rock Pass? Off the top of my head, yeah, I don't think there would be, but you'd have to get a lot of water there, right? So, but if you could somehow magically get the water there, it would be at Red Rock Pass, but it would be at a lower elevation because you've already got it cut down. Yeah, good question. Yes, question here.
We have the gravel from the Bonneville flood flow is still gravel. Could it have been some Missoula flood before that, and then Bonneville flood before it came to the top?
Yeah, the question was, in Lewiston, you've got the Bonneville floods clearly underneath the Missoula floods, but is it possible there were other Missoula floods prior to that Bonneville flood? Is that right? I'm not a good expert on the Missoula flood, so I don't know for sure, but I'm what I've read and what I know is that the Bonneville flood predates even the earliest Missoula floods. So yeah, we'd probably have to ask someone else to find out what the hard evidence is on that, but yeah, good question. Yeah, there was another hand up. Yes, ma'am.
So, I don't know if I missed it, but did you talk about what caused the sudden drop? Who pulled the plug? I know.
Oh,
I know what happened.
right,
With that breach.
right.
Was there something similar with the Bonneville?
Yeah, good question. And I actually meant to mention that. So the question is sort of what was the trigger for the Bonneville flood? We don't know. That's the real answer. There is an idea that if you look at the region around Lake Bonneville, you've got lots of active faults, including the Wasatch Fault. So one idea that's sexy and exciting, so people will take this with them because it sounds really good, is that there was a large earthquake on the Wasatch Fault or some other fault system, that the shaking from that fault would have caused Lake Bonneville to slosh and produce what's called a seiche, or like a set of waves sloshing back and forth. So if you already have Lake Bonneville near the tipping point, and now you get high wave action, you can overtop that divide, produce enough energy to cut down through it, and now the domino effect's rolling and the snowball. Yeah, so there's that idea. One other idea is that it got high near Red Rock Pass, but that loose gravel from the landslides and the alluvial fan, that the lake water was able to seep through it, saturate it completely. It washed out, and that precipitated the flood. And then the most boring, less attractive idea is the water just finally rose to the top, crept over the top. But once you get water moving down with gravity, it has erosional force. It's really the knife through the butter, if you will. So there's 3 ideas for you, but we're not sure exactly which one occurred. Sure, follow-up question, yeah.
I get that the idea that roughly the same period, there was a lot of extra water.
Yeah.
In the west. Was that true in the east too?
The question is, was the abundance of water in the west also true in the east? My guess would be the global climate was definitely cooler. So you would have had higher flows of water in eastern rivers. I don't know the evidence for that, but that would be my best guess. We don't have any evidence, to my knowledge, of large catastrophic breaching floods anywhere back east. Yeah, or like ice dams impounding rivers or anything like that. Not to my knowledge. So really good question though. Yes.
I don't think Bob's gotten any chat questions.
Okay.
Or is it, have you gotten any?
I don't have it up. Oh, I can see it now.
There are some questions from the Zoom audience. Do you hear me?
Yeah, go ahead, Bob.
Okay, a question from Greg, who says, you would think the volume of water from the Bonneville flood would drain the current day Great Salt Lake of the baseline salts that remain in the Great Salt Lake Bonneville salt flats environs. Why is there such a density of salts still existing today in the Great Salt Lake that weren't washed out during the Bonneville flood?
Okay, I think if I'm understanding the question, it's why is the Salt Lake so salty? Is that the question?
Yeah.
Okay.
Great question. Why are so many salts still existing today?
Yeah, it's largely a result of so the Great Salt Lake is saltier than the ocean. You've probably heard that before. Similarly, if you go to the Middle East, you have the Dead Sea, right? And the reason is climate. So much water is lost to evaporation that concentrates the salt content. When you evaporate water, you take water from liquid phase, turn it into a gas, but whatever mineral material elements are in the water, those get stuck behind. And so those get concentrated in the liquid part of the water. And so that's how the Great Salt Lake ends up so salty, is over the last, however many thousand years, 10,000 years or less, you've got a very dry climate that's causing the water that's left behind to become saltier. And the Great Salt Lake actually fluctuates in its salinity. In the springtime, it's less salty because it's getting more fresh water pumped in by the rivers and streams. Probably with the year we had this year, it's a little less salty. The Great Salt Lake actually rose, I think, 3 feet, something like that, just this spring. And then you get into the winter and the fall months, and it becomes a little bit more salty as less fresh water comes into it. So I hope I answered that person's question okay.
Thank you, Shawn. And here's a question from Deborah, who asks, was the Bonneville flood, or what was responsible for the width of the Snake River Plain?
Can you repeat? I didn't hear the middle part of that.
Okay.
Oh, the width of the Snake River Plain. Yeah, I got the question. So the question is, yeah, the Bonneville flood and the width of the Snake River Plain. Those are 2 different things. The Snake River Plain exists as a low topographic region because of the Yellowstone hotspot and the volcanic activity. So as Idaho was dragged over the hotspot, that produced initially rhyolitic eruptions, then basaltic eruptions. Ultimately, as each area moved off the hotspot, the area subsided, the weight of the basalt and the lack of heat in the crust allowed the area to sink. And that's why we have a low area or a little smiley face across southern Idaho known as the Snake River Plain. The Bonneville Flood and the Snake River only occupy the lowest portion of that area.
Okay, thank you. Those are the only two questions I got.
Great. Yeah, Mike.
So going back to your initial graph, Provo and the high stand, is that difference what?
Yes. Yeah, and I probably didn't explain that as well as I could have. So the question was the difference between the Bonneville high stand and the Provo, that is the flood right there. And then we stabilized right here because that's because at Red Rock Pass, the river, the lake, the flood had removed so much of that loose material that it encountered hard bedrock. And at that point, it lacked the energy and the erosive power to cut down through solid rock. It had removed all the loose material of the landslide and the alluvial fan. So that's why it finally stabilized at the Provo shoreline at about 4,800 feet. Is that what you're asking?
Yes.
Okay,
Exactly.
okay.
I was looking, that represents the volume.
Yeah. So the
And the elevation change.
yeah, so the lake drops about 300 feet, a little over 100 meters, enough water to fill Lake Michigan, and then it stabilizes. And then, you know, and we think that maybe there was, maybe the lake, you know, the Bear River's still coming in. So maybe there was a few little floods over the rim, but nothing like the Bonneville flood happened. And then you get to a point where the climate shifts, becomes drier and hotter, and everything starts, the basin starts dropping. We're evaporating more water, and now the lake's shrinking more or less over time. Yeah, good question. Yes, right here up front.
The flood had precipitated earthquakes because a lot of material.
Yeah, the question is, good question. The question is, could the flood itself have precipitated earthquakes in the region? Probably not the flood, but the lake did. So as the lake grew and the sheer weight of Lake Bonneville on the crust likely initiated earthquakes, just like in modern times when Hoover Dam was built down by Las Vegas and they inundated the Colorado River and created Lake Mead. The weight of all that water on the crust actually initiated earthquake activity in that region for like 30, 40, 50 years. Not big enough to be like destructive earthquakes, but felt and seismically detectable earthquakes. The flood itself, I mean, if you had a seismometer and the Bonneville flood came by, you definitely would have picked up a signal there, but not like a true felt earthquake, I would guess. I'm not a seismologist, so that's my best take on it. But yeah, interesting thought. Yeah, for sure. Yeah, Mike.
Kind of a follow-up on
Mhm.
Bob's question. Was there a rebound from all this weight of water being removed?
Yeah,
In these two, I mean, really very quickly, even between high stand and today.
right.
Not a lot of years.
Right. So Mike's question is, was there rebound? So there's this thing called isostasy. If you're not familiar with it, when you put weight on the Earth's crust, it subsides. So when glaciers covered it, the crust of the Earth actually sinks a little bit, or a big water body like Lake Bonneville. And when you remove that load, it actually rebounds. It actually rises, but it does so very slowly. So even today, like in Minnesota, which was covered in a mile of ice 15,000 years ago, even though that glacier's been gone for 15,000 years, that crust is still rebounding and rising a little bit. And so the shorelines around Lake Bonneville, some of them, they all have risen a little bit. And so when we talk about some of these elevations, they've been corrected a little bit for some of that rebound. And I think the rebound's on the order of maybe tens of feet, something like that. Yeah, maybe a little bit more. Good question. Yes, ma'am.
I assume there's still erosion happening. Is it the Texas still have those curves that you showed us, the high and low curves, still erosion happening?
Yeah, the question is the Snake River today still eroding? And that's a tricky question. when I look around Jackson Hole and this part of the Snake River, I'm like, yeah, like the river is pretty high right now. And it's carrying sediment. And if a river is carrying sediment and has velocity, it should be eroding to some degree. We go further downstream though, where I live in Twin Falls, that's a little different Snake River than your Snake River. So even though you and I are connected by this river, you're near its headwaters. It's pretty much unregulated except for the dam at Jackson Lake, I believe, for the most part. But by the time it gets down to Twin Falls, there's diversions, lots of dams, and so it lacks a lot of its power. So right now, where I live in Twin Falls, Shoshone Falls should be spectacular. It should be full tilt. People should be driving in from adjacent states to look at it. Right now, Shoshone Falls is, you know, like maybe worth the $5 if you're in the area. But normally, so if you take away all the diversions and the human constructs on the Snake River, it absolutely would be a strong, powerful, in some places erosional river, some places depositional river. But in modern times, we've sort of engineered some of that out of there. Yeah, follow up.
Reason I asked, the bridge does not look like it was state. Yeah.
Shawn?
My fault.
Yeah, the question was, the Prime Bridge in Twin Falls doesn't look safe, and she's concerned that it might fall over. Yeah, I do have a friend who works for Idaho Transportation Department, and they do inspect it annually. So I trust those engineers as far as I can throw them, I guess. But yeah.
She's thinking about.
Oh, the plunge pool there. Yeah, I mean, ultimately, to a geologist like me, it's all going to go at some point, right? Every dam, every human structure is somewhat ephemeral, but yeah, yeah. They're actually looking at building a secondary bridge downstream to deal with traffic flow. And anyway, side note there, but yeah, question.
The graph here where you have the Provo shoreline shown,
Yeah,
you got a gradual increase in the lake elevation.
yeah,
Is that due to rebound, you think?
that's what I think. It's not my graphic, so I wasn't sure, and I thought that same thing. So the question was why the slight increase in the Provo shoreline? That could be that isostatic rebound. You just took Lake Michigan off of that crust.
So
That's a tremendous amount of weight, and so the little bit of crust will rebound.
until it finds a new outlet, and then it starts flowing over that, and then you have a, excuse the pun, cascade event.
Right,
It goes faster and faster.
right. Yeah, and then, I mean, by the time you get to here, it's definitely, all the climate models show a drastic change in climate in here. So, yeah. I looked up, I don't know much about Lake Gunnis. I think this was just another shoreline where it stabilized for a period of time. But I'm still learning myself some of these things too. So
What's the Gilbert episode?
that's just, I think that was just a short little rise. I don't know much about that either. Yeah, there's a shore. This is the Gilbert shoreline. The prominent shorelines all have names. All the shorelines are produced when we have a period of lake level stability. And then even though it's smaller, even the Great Salt Lake, which, you know, we just kind of pushed to the side, it's still a large water body, and you get the wind pushing on the face of that lake, and you get large 20-foot waves that cut into the hillside, cause a lot of erosion, and that's what creates those benches or those shorelines. Yeah, good questions there. Yes, sir.
Just looking at this chart. I wonder if that's part of where all the water's sure that the Buenas are also seeing this.
Yeah, absolutely. The question was, well, I didn't let you ask your question, or.
So I'm more of an observation.
Okay, the observation was that the Uintas were extensively glaciated, and this time interval is a time of extensive glaciation in the west. And so the glaciers would have produced a lot of water that would have gone into the basin and it helped the lake rise. And that's absolutely true. You can see Little Cottonwood Canyon near Salt Lake City. is beautifully U-shaped. It just looks just like, you know, Cascade Canyon up here in the Tetons. There you would have had glaciers going into the lake. So there were glaciers in the Wasatch and not the Uintas, but in the Wasatch that went right into the lake. There were icebergs floating out on Lake Bonneville at times, which is cool to think about.
Hey, Shawn,
Yes, Bob?
we have another question from the Zoom crowd. A
Sure.
question from Nan, who asks, do you know of any deposits in the Pacific Ocean correlated with the Bonneville flood?
I remember reading something about some seafloor sediment cores that they were able to trace back to that. So I'm going to say I believe so. Does anyone else have knowledge about that? Or okay, so heard some whispering in the crowd. So I believe that they can trace the Bonneville flood deposits. Now, by the time you get down to the mouth of the Columbia, you've lost a lot of the big boulders, but definitely the sand and the finer grain sediments. I believe there were some studies where they've actually found those there. So,
Okay, thank you.
yeah, good question. And then one more question here in the audience, follow up.
The final drop there. Current level,
Uh-huh.
get into that Red Canyon neck piece.
Red Rock Pass, yeah.
Is there some geological hard features that are
Yeah, the question was, like, I believe the question is something about why Red Rock Pass stabilized at that elevation?
what got eroded away?
Right. So the thing that got eroded away was the slide in the alluvial fan material. And this is my attempt to make a good graphic, and I don't think I've succeeded fully, but hopefully it gives you the idea here. But then eventually you hit just below the valley floor here, solid rock. And that solid Paleozoic rock limited the extent of the Bonneville flood. If it was able to just keep cutting down through soft material, perhaps most of the lake gets emptied. But it ended at the Provo level because that was the amount of material it could easily erode at Red Rock Pass. And so it stabilized right there. So there's the Provo shoreline, basically the bottom of the valley floor at Red Rock Pass.
Had to erode down the Provo level.
Oh, right.
What got cut?
Well, it didn't get cut at Red Rock Pass. At that point, the lake's just dropping. So I get your question. I apologize. So when we go from here down to here, that's just the lake staying in its boundaries. Yep, not spilling over, but just dropping because of less influx and more evaporation. Yeah.
The slope of the curve is sort of proof of that.
Yeah, right. Like that's a straight drop there, and these are more gradual over time, right? So that's that event right there. Even going from Provo down to Gilbert, that's still taking what, like 2,000 years ish, something like that. Whereas this is like more or less instantaneous geologically. So good stuff. Did I survive all the questions?
Yeah, you did.
All right. Thanks.
So Shawn, we have a small token of our appreciation for a really terrific talk. And I did watch the YouTube video, and this is like, I got double my money. This is great.
The YouTube one was like my first little quick side note. So doing all the field videos, and then I thought, the Bonneville flood needs more attention. So I just did this really quick, hasty thing, sitting in front of my computer, put it out on the internet, and it's like one of my better videos in terms of views, but it's actually, I need to replace it with this one. This one, I think, a little more polished. So yeah. So
Good question. How did you get here?
just my name.
Okay.
So yeah, if you just look for my name, yep.
Yeah, or Bonneville Flood. I think that's how I got
Yeah,
there.
well, that's the crazy thing is you Google Bonneville flood and my crappy 20-minute videos.
It's
only
number
get
one.
like, yeah. So again, the Missoula flood's got books and National Park Service.
So again, our next talk is not a Tuesday, it's a Thursday, July 6th. This is your chance to get autographed copies of these books. And like I said, I've used the Geology Underfoot books. They're great. So again, thank you so much, Shawn. The usual drill with the chairs. There's still some food to eat. We have a few minutes before we have to clear out. And thank you, everyone, Zoom and present, and mostly thank you, Shawn.
Yeah.
I appreciate it. You did a great job. Really.
Thank you.
Very much.